Okay, this is a question which is asked by a student. It's a very nice conceptual question. So you can just read it and you can pause the video actually and read. I'll go over to the solution. So here it is given that there is a long solenoid and then there is a loop which is kept, and in this loop there are two identical bulbs, but then there is a shorting wire which is kept. Now as soon as the shorting wire is kept, what happens to the bulb A and B? So that is what we have to discuss. So let us draw the solenoid first, the cross section of the solenoid, and there is a into the plane magnetic field. And outside the solenoid we have a loop. Let me just darken this. Yeah, much better. So this is the conducting loop, and in this conducting loop there are two resistances or two bulbs which are kept. Definitely if the magnetic field is increasing, then you can say that there is resistance R and there is resistance R. So because of the increase in magnetic field, there is a flux change because in this red loop, red conducting loop, and so current will be developed. Now obviously the current direction can be determined by Lenz's law. So if the magnetic field is increasing and it is into the plane, so the current will be anti-clockwise, and the same current will be flowing through both the bulbs. Let me just know which bulb is okay. So this bulb is A bulb, this bulb is B bulb. So since same current will be flowing through both the bulbs will be equally bright before keeping the shorting wire. Now let us say that we have kept the shorting wire. Now because of the shorting wire the current will change. So let us remove the current that we have drawn, and the shorting wire is kept something like this on the side of the B. Okay. Now what will happen? Whether A bulb will glow or B bulb will glow or none of the bulb will glow. So that is what we have to see. The thing is that the shorting wire is of zero resistance. Now let us consider a loop and apply Faraday's law in that. So what is Faraday's law? Integral of E dot dl is equal to minus d phi by dt. Now we will assume some current also. Let's say here the current is I1 and here the current is I2, and this current is then I1 minus I2. Now we are going to apply the Faraday's law in this white arrow indicated loop, and we will be circulating also in the direction of this white arrow, and we will write integral of E dot dl is equal to minus d phi by dt. Now as you can see, this white arrow loop has got zero flux through it because the flux is there only in the yellow boundary region. The magnetic field is there only in the yellow boundary region. So in this white arrow loop the flux is 0. So d phi by dt is 0 for this loop. And since d phi by dt is 0 for this loop because there is no phi, integral of E dot dl is 0 for this loop. Now if integral of E dot dl is 0 for this loop, then let us circulate in this loop, write the integral of E dot dl and equate it to 0. So what we will do? Well, we'll start from this point P. We will go to Q along this white arrow line. So going from P to Q we encounter a resistance R. So integral of E dot dl from P to Q along this white loop will be equal to plus I1R, and then we will go from Q to P back again through this white loop through this I2 current path, or you can say through this blue path, to come back to point P. So integral of E dot dl from Q to P along this blue part or blue wire will give a 0 value. Why? Because moving along this path is like moving along the 0 resistance, and so there is no IR involved because R is 0 for this blue wire. So this is the complete integral E dot dl along this white loop, and that is equal to 0. Now from here what do we get? From here we get that I1 is 0, which means there is no current I1. Okay. So this is conclusion number 1. And as soon as we see that I1 is 0, we can say that the bulb B will have no current. So the bulb B will then not glow after shorting the wire. Now we have to talk about bulb A. So let us just remove this path and consider another path which involves bulb A. Okay. If previously the magnetic field was changing at a rate of dB by dt, and because of which there was a flux change of d phi by dt, the flux is there only in the yellow region. Alright, so we have completely removed this loop. Now we will consider another loop, and also now we know that I1 is 0, and so we can now change our currents and say that there is only one single current because the other current is 0. So we can say that there is only one current I, and because there is no current through the bulb B, the entire I will go through this only. So this is what is this I, and this current is 0. Alright. Now let us do the circulation along the blue arrow indicated loop. White arrow indicated loop. And we will do the circulation along this loop and write that integral of E dot dl along this loop is equal to minus d phi by dt. So we will start from this point Q. We will go anti-clockwise up till point P and write integral of E dot dl, and that will be equal to plus IR, where R is a resistance of bulb A. Then from P we will go back to Q via this blue wire which is resistanceless, so across which there is no integral of E dot dl because there is no electric field, because the resistance is 0, so there is no electric field required to drive the current. The electrons will flow simply because of their inertia, because there is no resistance to their path. So 0 resistance along this blue path. So we started from Q, we moved to P, now we are back to Q again, and we have done the circulation along this white loop. So let me shade the area of this loop so that we can calculate the rate of change of flux through this loop. So this is a loop that we are talking about, and through this loop integral of E dot dl we have already written, and we will equate it to minus d phi by dt. As far as phi is considered, phi is there only in the yellow region. Alright, so only in the yellow region it is there. So phi is equal to the B in the yellow region multiplied by the area of the yellow region. Now we will put a minus sign here on the flux. The reason is that we are doing anti-clockwise circulation. So according to right hand thumb rule, the area vector will be out of the plane, whereas the magnetic field is into the plane. So that's why the flux is minus BA. B being the magnetic field in the yellow region, and A is the area of the yellow region where the magnetic field is present. So what do we get? We get that IR is equal to dB by dt into A, or this current is equal to dB by dt into A by R. So definitely there is a current in this wire which in this bulb A. So definitely there is a current. Now this current is double of the initial value before shorting this red wire. Why? Because before shorting, what was the situation? Well, before shorting there was equal current through A and B, and there was same EMF. So let me just show you what was happening before connecting this or shorting this red connecting wire with this blue wire. What was the situation before? So situation was like this. Just we had this conducting wire and there was a same current. Let's call this current as I old. And if you do the circulation along this red wire in anti-clockwise direction, you will get that integral of E dot dl. The circulation is equal to I old into the resistance of A plus I old into the resistance of B, because before shorting with the blue wire there was same current I old in both A as well as B bulb, and so this was 2 I old into R, which is equal to minus d phi by dt. We are circulating along this red loop, so this is the area through which we have to calculate the flux and its rate of change. However, out of that entire shaded area, only the yellow part had the flux, and we have already understood that okay, for the yellow part the flux can be written as minus b into a, again because we are doing anti-clockwise circulation. So 2 I old into R is equal to dv by dt into A, and so the old current was actually half of the new current through the bulb A. Alright, and so what will happen? The bulb A will glow brighter because of now more current because of the shorting, whereas bulb B will lose the entire current because all the current which is flowing through the bulb A will now pass through that shorted wire of blue color, and no current will pass through this bulb B. So bulb B will lose all its brightness. So this is a solution of this question.